Okay, so let's consider the following example. Prove that the set of vectors b equals 1, 1, and 4, 3 is the basis of R2. So solution. Now, a basis of a vector space, this is a vector space over here, is a subset of your vector space that satisfies two conditions. So we have to satisfy two conditions, but we'll see that it'll really only be one. So B must satisfy one, linear independence, and two, it should span the vector space. So span of B should be equal to all of R2. Okay? So that's the two conditions. However, the dimension of R2 is 2, and the number of vectors in B, so I denote the number of vectors of the number of elements of a set by writing something similar to absolute value, is also 2. And in such a case, it's enough only to check one of these conditions. So if I don't check the span, but I do check linear independence, then we'll get the span condition. Or if we don't check linear independence, but we do check the span condition, this will imply linear independence. So you really only need to check one of these. Now, another way to do this is just calculate the determinant of the matrix whose columns are these vectors. If the determinant's non-zero, then it's a basis. But this is only valid, that argument with the determinant, only if you have n vectors for Rn. In our example, 2 vectors for R2. So let's use linear independence. So solution. So we'll prove that these 2 vectors are linearly independent, and I'll do it from the definition. I could solve it differently. So let's solve A times 1, 1 plus B times 4, 3 equals to 0. Now I chose to write the vectors as column vectors. You could have written them as row, even though it is considered more precise to use column vectors. And we have 2 possibilities. Either A and B are only 0, and this will mean that we have linear independence, or there might be other solutions. So there's some non-trivial solutions. If we have non-trivial solutions, for instance, A equals to 2 and B equals to 5, whatever, or A equals -3 and B is 1, then we get linear dependence, which is very sad because that's not what we want. So I'm going to show that we only have the trivial solution. So let's multiply this out. So we get A, and normally we'll skip these steps. 4B, 3B equals to 0, 0. Let's add this up. So this gives us A plus 4B and A plus 3B equals 0, 0. And we can use Gaussian elimination, or we can just use sort of like, I don't know, just solving it, like common sense. So what we get here is A plus 4B equals to 0, A plus 3B. And we'll see a shorter solution afterwards involving determinants. And now I can ignore Gaussian elimination, right? I can just, there's so many things I could do. I could say A plus 3B is 0, so that takes care of A plus 3B over here. Or I could just subtract the equations. If I subtract, A minus A is 0, 4B minus 3B is B, equals to 0, 0 minus 0. So B equals to 0. On the other hand, if we look at this equation, A plus 3B, but B is 0, therefore A equals to 0. So we found that the only solution to this is the trivial solution, therefore, so let's write this down. So the only solution to the above vector equation is the trivial solution, a equals to b equals to 0. Therefore, b is linearly independent. And as we noted earlier, the dimension of R2 is 2, and the number of values in B is 2. Therefore, B is a basis. Right? This follows from the linear independence of R2. Let's see another solution using determinants. But this solution is really only helpful if we already learned about determinants. So B equals to 1, 1, 4, 3 is a basis of R2 if and only if, excuse my handwriting, the determinant of 1, 1, 4, 3 is non-zero. So let's check. Let's calculate the determinant of 1. We can also, it's pretty easy to see that these vectors are linearly independent. I worked really hard and I wrote out the definition, but for two vectors, linear independence just means that one vector is not a multiple of the other. Okay? So they span the entire plane, R2. So here we get 1 times 3 minus 4 times 1 equals to negative 1, which is non-zero. Therefore, B is a basis again. So we've proven again that B is a basis of R2. Okay? And I could have done things differently. Right? There's so many ways to solve this, right? Another solution would be that we know that R2 equals to the span of 1, 0, 0, 1, right? That's the standard basis. Okay, now let's look at span of B. Span of B is just the span of these two vectors, right? The simplest solution so far is using the determinant. Now, this is equal to, I'm going to construct these vectors. That's the idea. Okay, so I'm going to copy this, and I'm performing something similar to elementary row operations. So if I subtract negative 3 of 1, 1, 1, the span is preserved. Okay, it's kind of like adding or subtracting a multiple of another row. But why did I do that? Because this is equal to negative 3, negative 3, and adding it to this gives me 4 minus 3 is 1, 3 minus 3 is 0. Okay, but I'm trying to obtain this. So now I can use the same trick again. So now let's take span 1, 1 minus 1 times 1, 0. Technically, I'm doing Gaussian elimination on the vectors. That's what I'm really doing. Okay. But this is exactly the span of the standard basis. And we're assuming that we know that the span of the standard basis is just R2. So if we sum up, we found that the span of B equals to R2. But as we mentioned earlier, since B has two vecters and R2 is two-dimensional, then if I prove this, I don't need to I don't need to prove linear independence. Therefore, once again, we've shown that B is a basis of R2. But we have to, explain the fact about the dimensions and the number of elements in B. So B is a basis of R2. Amazing. So we've done it yet again. So have an amazing day, and of course, happy linear algebra.